In this lesson, we're looking at solving exponential equations using logarithms. And really, the only other way we've looked at so far for solving an exponential function is by getting a common base on each side and then setting the exponents equal to one another. All right. What we're going to do today is basically look at examples where we can't do that. All right. When I can't get a common base and set the exponents equal to each other, that's when logarithms come into play. And once again, these are our three inverse properties of logarithms. The one that we're going to be really focusing on and using today is this one in the middle. Okay. To solve logarithmic equations, we used this last one because here the exponential function is undoing the logarithm. Well, now today we're using this one because here the logarithm is undoing the exponential function. That's what we're looking at today. We're going to take exponential functions and solve them using logarithms. Okay. So when we do this, the first thing we do is we isolate the exponential part of the function. So whatever's being raised to a power, we got to get that thing by itself. All right. We move everything else to the other side of the equation. We get the thing being raised to a power all by its lonesome. All right. Then we're going to take the logarithm of each side. We're going to use that middle property to undo the exponential functions. We're going to use a logarithm to get rid of the exponential function, and then we're just going to solve what's left. Once the exponential function has been eliminated, we're going to see what we have left, plug it into our calculator, and go from there. Okay? For example, if I look at this one, I've got 5 to the a equals 120. Again, I can't write these as a common base. There is 5 to no power that I can think of will give me a 120. 5 to the second is 25. 5 to the third is 125. So it's kind of in between there. It doesn't work with that first method. So this is why we use logarithms. So the first thing I do is isolate the exponential part of the function, which it's already isolated. The thing being raised to a power is already by itself. So now I have to undo 5 raised to a power. Right now I have 5 raised to a power. I want to undo that. And if I want to undo 5 raised to a power using a logarithm, I have to use log base 5. See, remember the bases here have to be the same. That's what this rule up here is saying. It's saying, hey, when the base of the logarithm and the base of the exponential function are the same, they cancel out, and I'm just left with the exponent. So here the base of the exponential function is 5, so I need to use log base 5 in order to get rid of this thing. All right? Whatever I do to one side, I also have to do to the other side, so I have to do log base 5 to the other side as well. So now what happens is log base 5 and the 5 cancel out, so I'm just left with an a. Over here I have log base 5 of 120, and that is really a job for my calculator. Remember, when I want to plug this thing into the calculator, I just do the natural log of 120 divided by the natural log of 5 using my change of base formula. Okay, so I go ahead and plug that in, and that gives me approximately 2.975 when it's rounded off. Okay, and so this is my answer, and it should make sense because when you think about it, 5 to the second power is 25, 5 to the third power is 125, so I'm somewhere in between there, but I'm obviously closer to the 125 than I am to 25, which means that the a value has to be closer to 3 than it is to 2, so 2.975 makes sense. And if you plug this back in, it's not going to give you exactly 120 because I rounded this answer off, but it's going to be very, very close. Okay? If I take a look at the next one, again, if I want to undo 6 raised to a power, I'm going to do log base 6 of each side. So let me rewrite this to give myself a little bit of space in front of that 45.6. To undo 6 raised to a power, do log base 6 of each side. And what happens is log base 6 and the 6 cancel each other out, so it leaves me with just an x. Over here, again, this is a job for my calculator. I'm going to plug this in using my change of base formula. I'm going to do the natural log of 45.6 divided by the natural log of 6. Okay, so now I plug this into my calculator, and it looks like it gives me approximately a 2.132 when it's all said and done. And you can plug that back in to check and see if it works. All right. Now, the interesting part about this is when I do these, I tend to choose a base that's going to cancel nicely, but I could have used any logarithm I want. Let me just show you that real quickly. I could have used the natural log for each of these. So like this first one, if I had 5 raised to the a equals 120, I could just take the natural log of each side, and now I just have to use properties of logarithms. Remember, properties of logarithms allow me to bring this a value out front and make it multiplication when I expand. So it becomes this. And so now when you think about it, I have a times the natural log of 5 to undo multiplication. I divide, so I divide each side by the natural log of 5. And you see what I'm left with is a equals the natural log of 120 divided by the natural log of 5. Well, that's what I did when I did my change of base formula. This is why the change of base formula works. Because properties of logarithms allow us to bring that exponent down in front of any logarithm, that's why we can change any logarithm to whatever we want and plug it into our calculator through division. Okay, and so it gives me the same thing. And I could do the same thing with the next one as well. I could plug this in and use my natural log, and you can see kind of how the change of base formula works when we do that. If I take the natural log of each side, I bring the x out front, and now I'm going to divide by that natural log of 6. Okay, so this is why the change of base formula actually works, is because it's the same process as solving using any logarithm. Okay, and so you can see I'm going to get the same thing there. But for the most part, with these really simple examples, it's probably easier just to use the base that I have written here. Okay. If I look at the next one, again, the exponential function's not by itself this time, so I have to get it by itself, so I'm going to add 2 to each side. When I do that, I end up with 5 raised to the w plus 3 equals 19. Now to undo 5 raised to a power, I do log base 5. Again, you could just use the natural log here and then go from there. When it's a simple example like this, you might as well just do the base that matches. So now here, log base 5 and the 5 cancel. Leaves me with a w plus 3. Over here, I have log base 5 of 19. And now I'm going to subtract the 3 from each side. And really, this just becomes a job for my calculator. When you plug this in, make sure you do the natural log of 19 divided by the natural log of 5, and then hit enter, and then subtract the 3, just because it makes things work out just a little bit better. When you do that, you should get a negative 1.171 when it's all rounded and settled down. Okay. If I look at the next one, again, the exponential part is not by itself, so I got to get it by itself. I'm going to divide each side by the 3. So now I get the exponential part by itself. This equals 9. To undo to undo 4, I have to do log base 4. Whatever I do to one side, I have to do to the other side. Okay, and so now again, over here, these cancel, leaves me with a 2x. Over here, I have log base 4 of 9, and now I have to divide each side by 2. Again, when you plug this into your calculator, kind of take charge of order of operations yourself. Do the natural log of 9 divided by the natural log of 4, hit the enter button, which gives you a 1.585, then divide that by the 2, and hit enter again, and you'll get a 0.792. Okay, because we want to have a lot of accuracy on these, because exponential functions, as soon as we lose that little bit of accuracy, they can become drastically different in the long term, okay, as we start increasing these things. If I look at this one, again, I got to get the exponential part by itself, so I'm going to subtract the 10 from each side. So I end up with 2 to the x minus 4 equals, that's going to give me a 72. And now to undo 2 raised to a power, I have to do log base 2. Whatever I do to one side, I have to do the other side. Over here, the log base 2 and the 2 cancel, leaves me with an x minus 4. And now I add the 4 to each side. Again, just be careful plugging these into the calculator. Kind of take charge of order of operations yourself. Do the natural log of 72 divided by the natural log of 2. Hit the enter button, and then add the 4 and hit enter again. Okay, so kind of do it in 2 steps there. Don't round anything off as you're plugging it into your calculator, but do it in 2 steps, and to 3 decimal places this rounds to 10.170. Okay, if I look at the next one, the exponential part here is by itself, so I'm going to take I'm going to do log base 30 of each side this time. Let me give myself a little space. So to undo 30 raised to a power, I don't know what I just wrote there. Let me try that again. Oh boy. To undo 30 raised to a power, I have to do log base 30 of each side. Whatever I do to one side, I have to do to the other side. Over here, the log base 30 and the 30 cancel, leaves me with an x squared. Over here, really, this is a job for my calculator, but then I'm also going to take the square root. And again, just be really careful plugging this into the calculator. Me personally, what I like to do is I like to punch in the natural log of 50 divided by the natural log of 30. And that gives me a decimal, and then I'm going to do the square root of the answer. There's a little button that says ANS on your calculator. If you do the square root of an answer, it gives you 1.072 when it's all said and done. Okay, technically it would be plus or minus that, so I should probably put that here. Almost forgot that plus or minus because I took the square root of each side. And we tend to throw out the negative answers here because we're used to solving logarithms. But that's not the case in this one because it's an exponent. Negative answers are fine. Okay? In an example like this one, the thing that becomes really tricky here is the fact that I have two different exponential pieces, all right? Now, granted, each of those exponential pieces is isolated, but the issue we run into is if we look at the left-hand side of this thing, the left-hand side would kind of want us to use log base 4 to undo it. The right-hand side would kind of want us to use log base 9 to do this side, all right? And so what we can do is we can choose either one of those and make one side cancel but not the other. The problem is that as we do that, and as we try to simplify this thing, one of those sides is going to have a fraction that represents our logarithm because we're going to break that down into a natural logarithm divided by a natural logarithm. And so what we do here, anytime I'm faced with the decision of having to pick one base or another, what I do is I don't use either of those bases, okay? So really, think about it. That's the most fair thing to do here. If one side wants me to use log base 4 and the other one wants me to use log base 9, the best thing I can do is say, okay, well, nobody's going to get what they want, and we're going to use some other logarithm. And the logarithm that I'm going to choose here is the natural logarithm. So here's what's going to happen. I've got 4 to the 2x equals 9 to the x plus 1. I'm just going to take the natural logarithm of each side. So I do the natural logarithm of each side. And now from here, it's properties of logarithms. So with properties of logarithms, I can take the exponents in there and bring it out front. So I can bring the 2x out front. That gives me the natural log, 2x natural log of 4. Over here, I can bring the exponent out front. That's the x plus 1 times the natural log of 9. So I'm using that property of logarithms that allows me to do that. And again, because this becomes multiplication, that's why I need to have parentheses here, because it's x plus 1, that binomial times the natural log of 9. So that's why the x plus 1 has to be in parentheses, okay? Now from here, I'm going to distribute. Keep in mind, if this was like 2x equals x plus 1 times 9, I wouldn't even hesitate. I would go ahead and distribute this 9. Well, I have a very similar situation here. I have the natural log of 9, which is really just a number, so I'm going to distribute that number here. When I do that, it looks just a little bit different. I get a 2x natural log of 4 equals, this is going to be an x natural log of 9 plus the natural log of 9, or 1 natural log of 9, all right? So when I distribute that, I leave it in terms of the logarithm, and that's pretty much it for that step, okay? So I can't really do anything else in terms of the distributive property. Now from here, again, if I were thinking about this example, if I had something like 2x equals x plus 9, if there were no logarithms involved, I would immediately try to get all the x's on the same side. I would subtract the x from each side. Well, it's the same thing down here. I want to get all the things that have x in it on the same side. So I'm going to subtract this x natural log of 9 from each side. Okay? And so when I do that, what I have left is I get 2x natural log of 4 minus x natural log of 9 equals the natural log of 9. So now I've got my x values all on the same side. So from here, what I want to do is I want to find a way to isolate that x value. The problem is, if I didn't have these logarithms here, I'd be able to combine these like terms and just have some value times x, all right? I want to leave this in terms of logarithms because I want this to be super accurate, so I don't want to plug this in until the very end. And so to isolate the x value here, what I have to do is factor it out. So I factor out the x. That leaves me with a 2 natural log of 4 minus the natural log of 9 equals the natural log of 9. So now what I really have here is x times a number. This whole thing in parentheses is just a big, giant, ugly number. If I plugged all that into the calculator, it would give me some decimal, all right? So what I really have is x times a number. To undo multiplying by a number, I just have to divide by whatever that number is. So if I have x times an ugly number, I divide each side by that ugly number, okay? So I do this. Whatever I do one side, I have to do the other side. 2 natural log of 4 minus the natural log of 9. Okay, that whole thing in parentheses, I divide each side by that. And so now what I'm left with here is I get x equals, so in terms of an exact answer, this is the natural log of 9 over 2 natural log of 4 minus the natural log of 9. Now I'm going to punch this into my calculator. The issue is punching this into the calculator can be a little bit tricky. If I want to punch this in the way it's written, I have to do the natural log, it'll give me a parenthesis, then the 9, I have to close that parenthesis, then do the division symbol, then do a parenthesis, 2 natural log, parenthesis 4, parenthesis minus the natural log, parenthesis 9, parenthesis, parenthesis. Okay? And if I miss one of those parentheses, it's going to mess this whole thing up. Okay? So I have to use parentheses to contain the entire denominator. I have to use parentheses for each logarithm to show what's inside the logarithm. So that becomes really cumbersome to plug into the calculator. So what we do instead is I rewrite this in terms of my properties of logarithms. So here I've got the natural log of 9 over. Down here, this 2 can be rewritten as an exponent inside the logarithm. So when I rewrite this as an exponent, it becomes the natural log of 16. And now from here, again, that denominator subtraction becomes 1 logarithm of the two things being divided. So this becomes the natural log of 16/9. Now this is a much easier job for my calculator when I pull this thing up. If I take this and plug it into my calculator now, all I'm doing is the natural log of 9, make sure you close the parentheses, divided by the natural log of 16 over 9. And close the parentheses and I hit enter. And it gives me about 3.819 is what we'll round it to. Okay? And so again, we want to wait till the very end to plug this thing in. But it's easier to plug in if we simplify using our properties of logarithms. And we can simplify as we're working through the problem to make this thing a little easier as well, which maybe we'll do in the next one. So if I take a look at this guy, again, the first thing I want to do here, because this one wants me to use a log base 3, and the other side would prefer if I used a log base 7, I'm not going to choose either of those. So in the grand scheme of things here, anytime you're forced to choose between two different bases, don't bother choosing, just choose the natural logarithm. Okay, so I'm going to do the natural logarithm of each side, so I take the natural log of each side, so I ln. And then from here, I can bring the exponent down, so I get the 2x plus 3 times the natural log of 3. Over here, I can bring the exponent down, the x minus 5 times the natural log of 7. Now I use my distributive property, so here I distribute, that's a 2x natural log of 3 plus 3 natural log of 3. Over here I have x natural log of 7 minus 5 natural log of 7. And now from here I need to gather my x's on one side and I need to gather my constant terms on the other side. And there's a couple interesting things that I should notice here. But the first thing is we generally try to bring this guy over to this side, and that would be fine. That means I'm going to bring this guy over to this side, and the end result there would be a 2x natural log of 3 minus x natural log of 7 equals a negative 5 natural log of 7 minus a 3 natural log of 3. And the thing you should notice here is how many negative signs there are. Okay, I've got a negative sign here, a negative sign here, a negative sign here. So all these minus signs, think about what minus signs do to us when we're dealing with logarithms. They either bring these things up as negative exponents, which is annoying because that gives us fractions, that's what negative exponents do, or subtraction of two logarithms ends up being division, which causes more fractions as well. All right? So if we want to avoid fractions in terms of logarithms, we tend to want to avoid negative signs. So what I can do instead of subtracting that x natural log of 7 from each side, let's bring the x's to the other side. Let's subtract the 2x natural log of 3 from each side. And I'm not necessarily doing that because of the x values. I'm doing that because of the other values. See, because then to bring everything to the other side, I'm going to add this 5 natural log of 7 to each side. And so what I end up doing is I end up reversing all of these signs from the previous option here. And so what I get is over on this side I have 3 natural log of 3 plus 5 natural log of 7. Over here I get x natural log of 7 minus 2x natural log of 3. So it's essentially the same thing that I had up here, but every sign is reversed. And that's the other thing. If you run into a situation where you accidentally brought everything to the wrong side and have all these negative signs here, it's pretty easy just to multiply each side of this equation by a -1. Take that extra step. If you multiply each side by a -1, what the end result is that I change the signs of each of these, and I'm back down to this guy. Okay? So be aware of those signs. Try to have as few negatives as possible. And so now as I start to solve this thing, I'm going to switch these around just because I like having the x on this side, and I'm sure most of you enjoy that as well. But now from here, I'm just going to factor out the x, and then I can divide by whatever's left. So here I factor out the x, gives me the natural log of 7 minus 2 natural log of 3. But now if I want to simplify this a little bit as I go, I can bring this 3 up as an exponent. That gives me 3 to the third power, which is 27. Over here I can bring that 5 up as an exponent, which gives me the natural log of 16,807. And now from here I can simplify this even more. Over here, look at this guy, natural log of 7. That 2 can go up as an exponent, so that becomes the natural log of 9. Over here I could multiply these things, so this becomes the natural log of 27 times 16,807 is 453,789. And now again over here I can simplify a little bit more. This becomes x, this becomes the natural log of 7/9 because I divide. And so now the end result, when I look at this thing, some of those properties of logarithms were kind of tough in terms of the values we got. But now when we look at the overall result of doing that, if I clean this up just a little bit, now all I have is x times a logarithm equals another logarithm. So it's much easier and it's much more presentable when we go to solve this thing. Now it should be much easier to see that I just have to divide by this logarithm in order to get x by itself. Whatever I do on one side, I have to do the other side. And now from here it becomes a job for my calculator. I'm just doing that logarithm divided by the other logarithm. Let me pull my calculator up so you can see how I plug this in. So when I look at something like this guy, again, I just do the natural log of 453,789, close that parenthesis, divided by the natural log of 7/9. And just make sure you close those parentheses. So it looks like it gives me a negative 51.829. And that's it. All right. So again, these look really complicated, but if you remember the basic steps, take the natural log of each side, bring those exponents out front, distribute, gather your x's to one side, gather everything else to the other side, factor out the x, divide by what's in parentheses, and you're on the home stretch. From there, it's just a matter of plugging it into your calculator, and the thing that makes that easier is using your properties of logarithms to rewrite these things. Okay?